Alright, so when we talk about bulky groups, what do we refer to? And actually I'm kind of making this video after the fact. I made a video on bulky groups, but this is kind of one that I found out when I was having a student who asked me like kind of esoteric, I shouldn't say esoteric, but kind of nuanced questions about bulky groups. So there's two ways that we can look at bulky groups, particularly around cyclohexane. The first is to look at just the number of carbon chains. And as students say it really well, it's kind of like the effective atomic weight of whatever's there. So if you look at a methyl versus an ethyl versus a propyl versus a butyl and so forth, the bigger the chain, the bulkier the group. And this is kind of how you would think about it, like it's a big chain. But let's say we take isomers of these chains. Let's say we take the propyl and we compare it to isopropyl. Well, the isopropyl is going to be bulkier, and the reason why our isopropyl here is going to be bulkier is by sheer merit of the fact that it's kind of got all the atomic weight clustered up against the carbon that's bound to our ring. So the length of the chain and the branching of the chain are going to basically dictate what's considered bulky. But that said, this is a very qualitative approach. What if we need something a bit more quantitative? This is where A-lists come from. And so the A-list is a kind of qualitative, semi-quantitative way of looking at the bulkiness of groups. So people have gone through and they've kind of used combustion analysis to figure out the size of these groups and from basically on the steric energies. And they've compiled a list saying that, okay, the more bulky the group, the bigger the A value or its value on the A list. Now, this is a nice semi-quantitative way of going through and figuring out. So when would you want to use the A list? Let's say we're comparing something like a methyl group to a bromine group. Which one's bigger? Well, bromine has the higher atomic weight, but the CH3 group actually takes a lot more space because it's got those like hydrogens hanging off of the central carbon. So which one's bulkier, this enormous bromine atom or this small but branched out CH3 group? And this is where you would start going to that list to say, okay, let's look at like things where we can no longer kind of do this back of the envelope calculation. Let's say we switch to CH2Br versus something like this isopropyl group. Well, the CH2Br technically has a branch coming off of it. It's got the Br, which is really big, but this has two CH3 groups. This is where you would consult those lists. So in general, you should be able to qualitatively say if a long branch or a branched alkyl group is bulkier relative to another one. But when we start kind of getting to very particular examples, we go to the A list. Now, what's the limitation of the A list? They don't consider electronic factors. So these groups were just kind of measured on their own. They weren't actually looked at in terms of how they interact. But there are definitely situations that we can conceive of where electronic interaction matters. Big one is tautomerization and hydrogen bonding. So let's say we take our ring and we have an OH group. And which one should be axial or equatorial? Well, this looks straightforward. This group is a lot bigger than this one. But alcohols can participate in hydrogen bonding. So these two can actually bond through this hydrogen. And because of that, we form a second six-membered ring. And so it kind of matters whether they're axial or equatorial as to whether or not you've created this stable second cyclohexane ring, well, six-membered ring, based on that hydrogen bonding. So you'll definitely find examples where the A-list makes incorrect predictions. And generally speaking, this is simply due to the fact that we're not really considering electronic effects. But again, if you need a good like semi-quantitative reference, that's what the A-lists are for.